Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi taala wabarakatuh. Rabbi shrah li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Alright, bismillah. Today we are going to learn about Fourier transform. Basically, this is the chapter number 7 in the textbook, a new chapter. Okay, so the outline of this chapter will be why we need to use Fourier transform. A periodic signal representation by Fourier integral, transform of some useful functions, how to transform it from time to frequency domain, and then what is the properties of the Fourier transform, and then the signal transmission through LTI, linear time invariant system, also about filters and its applications to communications. Okay. Alright, so previously we have learned about Fourier series. Okay, so we know that for Fourier series, we have a series of equation, whether in sine or with in exponential. So this series of equations will represent a periodic signal. Okay, so for a Fourier transform, it will be used for a non-periodic or a periodic signal. So that is the difference. Okay, so how to convert the Fourier transform? We will use this formula. The frequency in time domain will be multiplied in E minus j omega t. Okay, so if you can remember, this equation also being used for the previous chapter, which is the Laplace transform, where the functions ft multiplied by e minus st. So this time we will using j omega. Okay, so for Laplace we use s. Okay, that is the difference. And then for Fourier series, we will have a harmonic or series of equations which having an equation or coefficient and then the function. But for Fourier transform, we will have a continuous sum equation. That means even it's aperiodic, but we will continuing to convert and add. Okay, so the applications for Fourier series usually in some things that have a harmonic or repeat, such as vibrations analysis, acoustics, optics, or signal processing. And for Fourier transform, we will use it for a image compression, filtering, and image analysis, where the signal is not periodic; it's aperiodic. Okay. Alright, so what we are doing in Fourier transform, basically we will partition the complex problem into simpler ones or small equation. The simpler problem are then solved, and the total solution becomes the sum of the simpler solution. That means we will divide it, convert, and then we sum of the simpler solution. Okay. We may have insight into the simpler problems and can thus gain insight into the complex problem. Okay, so what we are going to do is we will analyze part by part, and we see what is the insight, and then we will combine it to become a complex problem. Okay, so mathematics will be a means and to solve a certain signal and system analysis. Okay, so that is our jobs as an engineer, to use these mathematical procedures. Okay, for Fourier transform, basically there will be requirements. Okay, the problem can be expressed as a number of simpler problems. That means we can divide it into small problems. The problem must be linear, such that the solution for the sum of function is equal to the sum of the solution considering only one function at a time. That means that according to the linearity properties, we can add the output will be equivalent if we add the input. Okay, the third one is the contributions of the simpler solutions to the total solution must become negligible after considering a few terms. That means it will considering an adequate accuracy. Okay, so that means we will not add more terms to the solutions. Okay, the added terms is negligible. Okay, all right. So this is how we convert from time domain to frequency domain. Basically, if we have a signal which has a few combination of signals here, so we can find the frequency of each of this signal by transferring it to Fourier transform. Okay, so in this signal we can see at what frequency this signal exists. Okay, and so does the second example, and the third example we can check the frequency of each signal by considering the transformation in Fourier transform. Okay, so this is in frequency domain. Okay, absolute value or the amplitude, and then this is the signal. Okay, so usually we will have a mixture of signals. That means we are going to have a mixture of different frequency. Alright, so again, some simple time functions can be transformed into Fourier transform. That's why we choose to have a chunk of it and then combine. Alright, and then the examination of both signal and system in the frequency domain gives insight that complement those obtained in the time domain. Okay, so we can have this concept of duality where the time domain and frequency domain can be interchanged. Okay, the function. Alright, so for the Fourier transform, the condition is must be a continuous time signal t that has a finite energy. Okay, so finite energy means if we do this test, the function squared, it has a finite number, okay, less than infinity. Okay, and it also can be applied in this formula, which is to find the function in Fourier transform. We will integrate from minus infinity to infinity the function multiplied by e minus j pi ft dt. Okay, so in general, if we have this function xf, it will represent the absolute value of this function. That means the amplitude or magnitude, we can call it the same. And also there is a phase here, ej phi xf. Okay, so phi xf is the phase spectrum of the signal. Okay, so this is the magnitude or amplitude, and then this one is the phase. Okay, alright, so again, if we could recall the function of Laplace, and this is also we are using the exponential in Fourier transform. Okay, but this time we are going to use the j 2 pi f, or sometime we will use as omega. Okay, so if we transform from time to f, okay, one side it will call ft. If it's inverse frequency to time, it is inverse ft. If we use this symbol, both side it's called ft or inverse ft operations. Okay, that means it can be two functions from time to f and from f to time. Okay, let's say we have this rectangular pulse. Okay, so most of the examples, okay, the easiest one we are using the rectangular. Okay, so this is the rectangular. Okay, so if you can see here, the amplitude is a, and then the size of the rectangular is tau. Okay, so this means that this is the size of the rectangular tau. Okay, to the right is tau over 2, and to the left is the minus tau over 2. So this is the size of a rectangular. For example, this is 4. Okay, let's say. So that's mean this is 2 and 2 with the size of A. Okay, if it's not mentioned here, that means it's equivalent to 1. Okay, but the size of it is rectangular, t divided by 4. Okay. Alright, so now we want to know what is the Fourier transform of a rectangular. So we will use the formula, the function, okay, multiply by the equation. Okay, so now we have the functions is actually a, or we can put it outside, a coefficient. Okay, it can be 5 or 1 or anything, multiplied by e minus j 2 pi ft. Okay, so we integrate this from the range minus tau over 2 to tau over 2. So the function will become this one, a e minus j pi tau minus ej pi f tau divided by e minus j 2 pi f. Okay, so we know that e and this one is equivalent to sine. Okay, so we simplify, this will become sine pi f tau divided by pi f. Okay, and sine pi f divided by pi f is equivalent to sinc function f tau with the amplitude a. Okay, so this is the function in frequency domain. Okay, so whatever the value here, okay, the size must divided by tau. Okay, and then this is the amplitude, and for the sinc function it will be decreasing until infinity. Okay, alright, so with this symbol, that means this is the magnitude or amplitude spectra, and this one is the phase spectra. Okay, so for the phase spectra, we'll have to plot it for each of the tau. Okay, 1 over tau, 2 over tau, 3 over tau, and so on. Okay, observe that the width of the main lobe of x increase as the pulse width tau will become narrow. Okay, alright, so the second example also the same. This is the function rectangular, and then in frequency domain it's a sinc function. Okay, but this one using omega. Alright, so the next one is the exponential signal. Okay, the next popular signal will be exponential. Okay, so we will convert the signal to a function f, delta f minus fc. Okay, so means that if we have a function in exponential, in frequency domain it will become a delta. So this is a delta function with the value of fc. This is the value of fc, depends on the j 2 pi fct. Okay, so means if you have a exponential function and then you make the format like this, okay, and to identify what is the fc, and you know that it will be located delta at the function fc. Okay, so this is the derivations. Okay, so this is the derivations of the function e exponential EAT, and then you multiply with the formula here. For this one we have two parts because it's an absolute value. That means we have two function of exponential, and then when we solve this one, we will have 2a squared plus omega squared. So this is different with the original e j2 pi ft. Okay, this is absolute value. Okay, alright, so the next common signal is a sine signal or signum signal. Okay, so for a sine signal or signum, it can be defined as 1 for t larger than 0. So 1 will be t larger than 0, and minus 1 for t less than 0. Okay, so this is the definition of a sine or signum function. Okay, so what we have to do is now we want to multiply it. Okay, so for this one we will have to put some function here, and then you will integrate it part by part, and this is the function in frequency domain. Okay, alright, the next one is the impulse. Okay, so impulse, we know impulse have only one value here at the point, certain point, or it will be means as 1. Okay, the unit impulse contain all frequency with equal magnitudes. That means we want to find the function in time domain, so we multiply it with e minus j omega t, and what we have, it will become 1. So impulse in frequency domain, it will become straight line or DC. Okay, 1 with the value of 1. Alright, so actually this transformation pairs is table in the formulated in a table. So this table will be given in the exam. Okay, so you don't need to remember. Okay, so for example, just now delta function is a can be vice versa. Okay, so a delta in time domain is a DC signal. Okay, so this is the relationship. And then we also saw just now that a rectangular in frequency domain is a sinc function. It also can be vice versa. If a time domain is a sinc function, in frequency domain is a rectangular. Okay, all of it is vice versa. Yeah. And then if we have a triangular in the frequency domain, it will be sinc squared. Okay. Okay, so we have to consider if this is tau in the frequency domain, the tau divided by 2, and also this one, tau divided by 2. Just follow this formula. Okay, and then for exponential e minus at, just now we also saw that the function in frequency is 1 over a plus j to pi f. Okay, so this is a. Okay, so whatever the value a here, you have to substitute here, plus j2 pi f. Okay, and then we also saw that there is e minus a absolute t, where we have both side. Okay, exponential. So in time domain, in frequency domain, it will become 2a squared plus 2 pi f squared. Okay, and we'll also just now saw that an impulse is a 1. Okay, so these two is actually the same. In impulse become DC 1, and impulse in time will become 1 in frequency domain. Alright, so this is also vice versa of this one. A sinc function will become a rectangular. Okay, and also the rest of it we also not shown in the example just now, but we can check using the formula. Okay, for a sine and cosine, usually we will use the similar 1 over 2 e j2 pi fc plus minus j2 pi fct. Okay, so this is the signal delta is a DC. Okay, for a cos is a delta here. Cos, okay, cos, it will become delta, but the size of the amplitude will become half. Okay, and then we have sine. Okay, and it will become 1 over j2 pi f signum. This one, j2 pi f. Okay, this is sine function. And then this is also rectangular. Okay, so it will become sin function. And also this one is a triangle, become sin squared. Okay. Okay, so this is also the example of the table. It will shows you the same, but this one using omega most of it. Okay. Alright, so just now is the basic pair. Okay, now we will learn about properties of Fourier transform. Okay, so the first properties, it is a linearity. Okay, so I have mentioned in the first part just now, we want to chunk this signal, okay, into different functions. Okay, so what we have to do, this one can be added to this one, so it has to be linear. Okay, so when we have two function, okay, when we transform, it will be individually transformed and added. Okay, so at the end it will transform individually and added. Okay, that is linearity. Okay, the second one is the time shifting. Okay, so if we saw that if the function does not start at 0, so it will start at t0. Okay, so what we do in frequency domain is we just convert the signal xt, but multiply it with a minus e minus j2 pi f t0. Okay, t0 is the values that shifted or delay. Okay, so to prove this, we can use this formula, the function minus e j2 pi f t minus t0. Okay, and then we will have the whatever transformation of the xf, but have to include e minus j2 pi f t0, the shifted value. Okay, this also having the same meaning. Okay, for frequency translations, if we have a function xt, okay, so it's actually inverse, right, duality, multiply by e j2 pi fct. Okay, so that's mean in the frequency domain we will have these functions shifted or delayed by fc. Okay, so this one multiply by e j2 pi fc, so in the frequency domain it will be delayed e by the values of fc. Okay, whatever the value here. Okay, that multiplication of signal by e j2 pi fc translates or shifted its frequency by the amount of fc to the right. Okay, okay, to the right. And then the next properties is convolutions. Okay, if we have the functions in time is convolve xt multiplied by convolve with yt. Okay, in time, in frequency domain, we don't have to do this one. This means if convolution, the definition is we integrate the functions, but the second function we will delay. Okay, so in the frequency domain, it will be simpler because we just have to multiply the function y, f, and xf. Okay, so the convolution in time equivalent to multiplication in the frequency domain. Okay, and then we have time scaling or frequency scaling. Okay, so if in the time domain the function is multiplied by a, in the time domain we will shift the function. For example, this is rectangular, so it will become sinc, but the f have to divide it by a, and there is also a coefficient that divided by 1 over a, the value of the scaling. Okay, so this is the proof that how xat will actually become the coefficient but divided 1 over a, and also the function f must be divided by a. Okay, so the scaling property states that if we compress a signal in time domain, so in Fourier transform or in the frequency domain, it will be stretched. Okay, similarly, if we stretch a time signal, it will be compressed in Fourier transform. Okay, so this is also true because we know that t is equal to 1 over f. Okay, so it's a vice versa, right? Alright, so the next properties is the differentiation properties. Okay, for example, we want to differentiate a signal in time domain. So in frequency domain, you just have to transform the signal xt, but you will multiply it with j 2 pi f. Okay, right. So this is the derivation. Okay, which is actually we will put it in the table, but to know how it works, we have to use the formula. Okay, so the differentiation in time domain is equivalent to multiplication by j 2 pi f. Okay, in frequency domain. Okay, so whatever the signal, transform it, but don't forget to multiply with j 2 pi f. Okay, so for the properties, we also have a table. Okay, the table is actually derived from the equation. Okay, so you can use the table directly in the examination. Okay, unless mentions to derive. Okay, so this is a multiplication example. This is the functions. Okay, the function says that for t larger than 0, the equation is e minus at. Okay, so the function can be transformed into Fourier transform f. So the transformation will become 1 over a plus I 2 pi f, or j here. Okay, you can use either I or j. So if we plot it, it will become like this. Okay, and for the second function is cos 2 pi ft. So this is cos 2 pi ft. If we convert in frequency transform, it will become 1 over 2 or 0.5 delta f plus whatever the function is, and there must be 2. Okay, so minus f and plus f. So this is the Fourier transform for the cos 2 pi f. Okay, the size will become 1 over 2, and this is f minus f and f. Okay, so when we multiply this one and this one, okay, so in frequency domain it will become convolution. Okay, so you just have to use the formula to transform it into convolution, and this is the result in time domain. Okay, so this is a larger versions of the Fourier transform table. Okay, exponential. Also, we can have t, e, at. There are two functions here, t and e minus at. Okay, so you have to use this formula. Okay, where it can also up to n. Okay, number of degrees of multiplication. Okay. Alright, so we have know the linearity. What is conjugate? Basically, conjugate is the inverse of that function in imaginary part. Okay, so if it's real, it will become x minus omega, the same, x omega. Okay, And this is the formula from time to frequency and from frequency to time, vice versa. Okay. Alright, the duality property basically means that if xt convert to x omega or xf, then xt will become x minus omega but multiplied by 2 pi. Okay, so here is the proof definition of inverse ft. Okay, so still we have to use this formula to find the inverse. Okay, so this is what we call duality property. Okay, so if a rectangular in time, the function in frequency domain will be sinc. Okay, so if the function in time domain is a sinc function, in the frequency domain is a rectangular, right? Okay, the same one. Okay, and then also we have scaling functions. We have a in time domain. In frequency domain, we have to divide it by a. Okay, and then this is the shifting property. Okay, basically if we shift the property with t minus t naught, okay, in time domain have to multiply it with e minus j omega t naught. Okay, this is the signal. Usually it's here, okay, but now it will be delayed by 3 tau divided by 4. Okay, this is the delay value. So what you have to do is you just convert the function to sinc, but the inverse or the shifted value you multiply by e minus j omega 3 tau divided by 4. Okay, the shifted value. Okay, this is the magnitude and also phase plot of this function. Okay, for the frequency shifting, so it's the same. So if a function is multiplied by e j omega naught t, in the frequency domain we will have to shift it by minus omega naught. Okay, in this function we have xt cos omega naught t. Okay, so cos omega naught t can be represented in exponential, become 1 over 2 xt e j omega naught t plus e minus j omega naught t. Okay, so that's mean it will have delay here, okay, with the value of omega naught in time domain. So in frequency domain it will be shifted by omega naught and minus omega naught. Okay, so this is the shifted value. Okay, this function is hx omega, but when it's shifted it will having this new value at the center. Okay, so this is shifted by omega naught and also minus omega naught. Okay, the size maintained here to omega. Okay, and also the output of it will become 1 over 2 or reduced by 1 over 2. Okay, this is the amplitude. Okay, this here is 2a reduced by half at the frequency domain will become a. Alright, so if we have functions with a rectangular, okay, and then this rectangular will be multiplied by cos 10t. Okay, so the xt is given here, rectangular t over 4. So the size will be 4. Okay, and it start at 0 because it doesn't shifted or anything. Okay, so 4. 2 to the right and to the left. Okay, so when we transform it will have sinc function. Okay, but the problem is it have this cos 10t, the multiplication. So if we want to convert this one, it will become shifted this frequency even it is already transformed sinc to omega, but it shifted by 10 and minus 10. Okay, how to do that? This function you shift by 10 and also this one shift by 10. Okay, So this is the result of a rectangular multiplied by cos 10t. Okay, so we consider it is shifted. Okay. Alright, so we also have a convolution property just now. So if convolve in the frequency domain, it will become multiplication. But if in time domain is a multiplication, in the frequency domain is a convolve. Okay, but divide by 1 over 2 pi. Okay, so we usually use this in the time convolution property for the impulse response. Okay, so this is the impulse response. Okay, so this is the derivation of the convolution property. Okay, so let's look this example. We have x cos 10t. So it's a multiplication. So in frequency domain, it will be convolve. Okay, this is multiplication. This one will convolve. Okay, so the next one is time differentiation. D dxt. So in frequency domain, we have to multiply it with j omega and then transform whatever the function is. Okay, and if time integration, we integrate this one, so we just transform but divide. Okay, for differentiation, multiply. For time integration, divide. Okay, so this is the initial condition of the function. Okay, you have to plus it, plus the initial condition of the function. So this is what I mentioned just now, integrations. We have to transform the function but multiply by 1 over j omega or divided by j omega plus pi, and then the initial condition multiplied by delta omega. Okay, so the rest is we have discussed linearity. So you can add this one, convert 1 by 1 and add. And then time shift means we will have to multiply with e minus j omega naught, j omega t naught. Time scaling, okay, divide it. Okay, and if it's shifted, okay, so multiply with e j omega naught t naught, but this one it also have a scaling, so divide it. Okay, and then the rest is a duality function and has been discussed. Okay, alright, so if a signal transmission through LTI system, usually we have this formula, the output multiplied by the impulse response and also the input. Okay, so let's say the HS or the H is 1 over S plus 2 and the input is j omega plus 1. J omega is actually an S. Okay, okay, so we want to find Y output is by multiplying the impulse response and also the input. Okay, so what it will become. Okay, so we just have to multiply this one and also this one. Okay, so when we multiply this, we will have this one separately and convert it into time domain. Okay, e minus t and e minus 2t. Okay, this is the A, just using the table. Okay, so this is the important formula for conversion of time domain and frequency domain. What is the equations and so on. Okay, this one the next one is we will learn about filter. Okay, so a filter separates the wanted part of a signal from unwanted part. Okay, so the ideal filter in its passband without distortion and completely blocks the signal outside its passband. Okay, so for a filter, for example, we want to identify the signal. Okay, so we need a filter for this one. So we will just stop the rest and pass this side only. Okay, so this is a filter design of a system example. Okay, so when we have this functions input, okay, goes to the output, we will need a filter to only display the signal that we want. Okay, alright, so basically the part that we want to pass the function, we call it pass band, and then there is a stop band where we reject this frequency. Okay, so this is frequency domain. Okay, so from pass to stop band, we call it as a transition band. Okay, so this is how it looks like in a spectrum analyzer. Okay, so the filter will only accept certain frequency and reject certain frequency. Okay, so for a low pass filter, so it will pass at low frequency, this is start at 0, and at high frequency it will stop. Okay, so this is the cut-off frequency. Okay, so the pass band and stop band is the differences. For high pass, at low frequency it will have reject and pass only at high frequency. Okay, we also have band pass, the combinations of stop and pass. Okay, but at band pass here at 0 it will have rejection, and high frequency it will stop or pass. Okay, okay, so this one is band stop. At high frequency it will stop the frequency, and here at 0 it will pass. Okay, so this is low pass. Okay, at low frequency it pass. This is band pass. At higher frequency it will pass. Okay, and band stop, at higher frequency it will stop. Okay, this is an example. Alright, so for an ideal low pass filter, we will have this rectangular, so mean we will have a sharp edges here, looks like a rectangular. So the impulse functions is the transformation in time domain. Okay, so if you want a ideal low pass filter as a rectangular, this one, so in time domain we have to perform the sinc function. Okay, so this is an examples of filters. This is the design of the filters using RC. Okay, if a high pass, we have to swap these locations. Okay, so the value of RC is will determine the center frequency. Okay, so this is a RLC design of filters. Okay, so this is how it's look in the spectrum analyzer, and then this is the magnitude or amplitude spectrum, and this is the phase spectrum. Okay, so again, if you want to have a ideal filter like this rectangular, we will have the sinc function in the frequency domain. Okay, so the next thing is the bandwidth. Okay, so bandwidth is measured as the amount of data that can be transferred from one point to another point. Okay, so usually if we want to identify the quality of a network or internet connection, we will tell what is the bandwidth. Okay, so it usually the unit is bit rate, or measured in hertz also, or sometimes we call it bits per second. Okay, so it's actually the size or amount of data that can pass through the connections. Okay, so if you imagine the pipe is the amount of water that possibly can flow. Okay, but the amount of water that currently flowing, it's represent the bandwidth. Okay, so for example, this is a signal as look in the spectrum analyzer. So it is appear at this certain frequency to this frequency. Okay, so the size that it can be transferred information or data is called the bandwidth, right? Okay, so how we measure a bandwidth is from the F1 to F2, the one that exists in the or pass in the frequency functions. Okay, we also have a 3 dB or half power. Okay, half power means it's measured at A divided by 2, this size. This is half power bandwidth. Okay, or 1 over square root 2 is actually in dB is 3 dB. Okay. Okay, so this is example if you want to measure the bandwidth for digital communications. So usually we will measure the central or main spectral lobe. Okay, so this is the most signal is contained. Okay, alright, so this is some of the bandwidth recommendations for a certain applications. So this bandwidth recommendation is decided by the FCC in international level or MCMC in the Malaysian level. Okay, alright, so that is all about for the frequency transform. I will continue for the revisions after this. Okay, inshallah, I hope you can contact me if you don't understand. With that, I end this lecture with wabillahi taufiq wal hidayah. Wassalamualaikum warahmatullahi wabarakatuh.